Okay, so it looks like we're now live. So again, welcome to the Schedule B seminar series for monsoons. And today we are joined by Dr. Ed Hathorne from the Geomar Helmholtz Center for Ocean Research in Kiel. And he will be talking a little bit today about silicate weathering around the Bay of Bengal. And so without further ado, Ed, would you like to start your talk?
Thank you very much. And yeah, thank you, Tara, Liviu, Peter, for organizing this. It's great. And I really enjoy being able to watch the recorded things. And I look forward to everything happening into the next year. Yeah, thank you again. Can you see my cursor? Can you see my screen? I guess you can hear me fine. So
Yeah.
without further ado, I want to talk to you today about tectonics, global climate, and the monsoon, and specifically silicate weathering around the Bay of Bengal. And this is work mostly done by a PhD student who's finished now, Lisa Brettschneider, who is working with myself and Martin Frank here at GeoMar. But there's so many other co-authors that I have to thank, and I'll try and thank them as we get there. But if I forget someone, I'm very sorry. I'd also first like to thank all the people who helped me prepare a ancillary project letter, which is a little sort of drilling proposal to redrill ODP 758, which then got me a ticket to Goa. And there I met Liviu and Steve, and then we put the Indian monsoon proposal together, and then it got drilled. And I have to thank everyone involved with that, everyone who sailed on the ship, everyone who helped write the proposal, all the diplomats who helped us get permissions. Thank you very much. It wouldn't be possible without you. So moving on, a little bit of a slide about the motivation here, and this is a very recently published thing from the World Meteorological Association. It's basically an atlas of disasters, and this is the map for Asia. And you see here a lot of people have died in Bangladesh and Myanmar, and India and China as a result of storms and floods, many of which monsoon related. Most of the floods are probably monsoon related. And you see here on the right that the number of disasters is actually increasing with time in the last 50 years. And the dark blue, which is the floods. So this is also increasing. Now, thankfully, we're better at mitigating this over the last 50 years, and so less people are dying, but the cost of these disasters is steadily increasing. And so this is, just a reminder that we really need to know what's going to happen with the Asian monsoon going into the future, because otherwise it's going to cost us lots of money, at least, if not lots of lives. Okay. I'm going to talk to you today about clays, and this is a really nice picture I found. And clays are made of these sheets. There's tetrahedral and dodecahedral sheets, and then these sheets are layered up as sort of sandwiches. This is a German style sandwich with just one piece of bread, and then this is a everyone else style sandwich with two pieces of bread and another sheet in the middle, and then these sandwiches are stacked together to make clay particles. And this is a kaolinite here, and then here you see smectite, which has lots of interlayer water. Some nice pictures here, and these chlorite and illite are generally primary clay minerals. They're mostly produced by physical erosion of rocks, and kaolinite and smectite are secondary minerals. So these are produced by silicate weathering of primary rock minerals. I'm also going to talk to you today about radiogenic isotopes of these clays specifically. So a little primer on that if you're not an expert. So radioactive decay of a parent isotope to a daughter isotope is what we talk about when we talk about radiogenic isotopes, and we're looking at the amount of the radiogenic isotope versus a stable isotope in that system. And so we'll be talking today about rubidium and samarium, strontium isotopes, samarium, neodymium, lutetium, hafnium, uranium, and lead isotopes are the daughters we'll be looking at. And the reason we have these different systems is because different elements are more mobile than others. Say for strontium, for example, is much more mobile in the Earth's surface environment, and therefore it tells us more about somehow the weathering fluid, perhaps, than necessarily the host rock. Neodymium is very well behaved. It doesn't really, the samarium and neodymium are both rare earth elements, so they're pretty much not fractionated between different minerals normally, and therefore the neodymium isotopes pretty much tell you about the age of a rock, and also the clays and things like this. There's little grain size effects, whereas lutetium and hafnium are very different, and therefore there's a lot of mineral sorting, different differentiation of the minerals with different lutetium and hafnium concentrations, and therefore isotope ratios. And uranium and lead, all these elements are very particle reactive. Uranium is not. Uranium is actually very mobile, and therefore it's much more, the lead system is much more, let's say, not susceptible, but can be influenced by crustal processes. So what happened when over time, the Earth differentiated into a crust and mantle, and while it was doing this, some elements preferred to go in the mantle, some preferred to go in the crust. And so for example, samarium here is preferentially in the mantle, and therefore the mantle rocks are more radiogenic for neodymium, whereas rubidium is preferentially in the crust, and therefore crustal rocks are more radiogenic for strontium. The neodymium and hafnium isotope systems, we will talk about an epsilon unit, and this is basically the ratio we measure against the ratio of this CHR, which is not a place in Switzerland. It's the Chondrite Uniform Reservoir, which is basically trying to have a ratio for the bulk silicate earth. And we didn't do any correction for the change of this in time, because in the mid-Miocene, this is not so large. If you work in the Cretaceous, you probably need to do that correction. Okay, so I don't need to introduce this to this audience, but this is what the Asian summer monsoon precipitation and winds looks like. This is reanalysis data for June, July, August, September, 1998 to 2009. And what you can see here is the monsoon circulation, these southwesterly winds bringing moisture from the Indian Ocean across the Arabian Sea, dumping a lot of it here on the Western Ghats. And then you can see the core convective region with the most rainfall is here over the Bay of Bengal, into Myanmar, Indo-Burman ranges, into Bangladesh, and along the foothills of the Himalayas. I just want you to keep this in mind as we go through the talk, that this really is where the rainfall is 18 millimeters per day, which is crazy. The Bay of Bengal is dominated by Himalayan sediments. So all this rain, all this runoff feeds some of the biggest rivers in the world, and they have the highest sediment load in the case of the Ganges Brahmaputra. There's a greater than symbol here because we don't really know. It's a lot. It's more than 1,000 megatons per year. And all this sediment ends up making the Bengal fan, which is the largest accumulation, and the Nicobar fan, largest accumulation of sediments on the globe. The rock types around the Bay of Bengal are quite distinctive. You can see these little numbers, maybe these are neodymium isotope values. And I don't expect you to read all these, but basically what I want to show here is that the different rocks have distinctive values, and this is transported to the bay, and we have a sort of east-west divide here in the bay with surface sediments values. So here, more in the west, you have much more unradiogenic neodymium values, more reflecting the high Himalaya, and also the very unradiogenic rocks from the Indian subcontinent. Whereas here in the east, we have more radiogenic values, reflecting a mixture of more mafic arc sort of stuff that comes from the Indo-Burman ranges, which have also the arc mafic rocks from the high Himalaya and the Tibetan series here along the Sutra zone. And I just want you to bear that in mind as we go through the talk. So the geological carbon cycle, this is something we all care about. Atmospheric CO2 is a very important thing, and it is basically determined by the balance between outgassing from volcanic rocks, from volcanoes, and metamorphic activity. And then it's the sync term is silicate weathering and organic carbon burial. So silicate weathering basically happens when you take carbon dioxide and some water and make carbonic acid, and you have a calcium aluminosilicate rock. And then you end up making calcium, some alkalinity, bicarbonate, and this aluminosilicate, which is a secondary clay. And so by looking at the secondary clays like kaolite and smectite, by looking at the clay minerals size fraction, I guess it'd be really nice to separate them, but we can't. But so we're talking about size fraction. By analyzing the size fraction of clays, we can see where this weathering action is happening, what sort of rock types are being weathered and turned into secondary clays. I should say that lots of people have talked about this balance being affected by mountains. More higher mountains, you have more erosion, you can get more weathering. You can also deposit more sediments, which can bury more organic carbon. And volcanic rocks, although the volcanoes are outgassing CO2, volcanic rocks are very easily weathered, and they can also enhance silicate weathering by having a large amount of basalt on the Earth's surface. All this sort of is quite a hot topic now, talking about weatherability. And so Claves-Rugenstein and others in a paper a couple of years ago were trying to work out how you could change the atmospheric CO2 concentration, but not change the silicate weathering flux. And so they did this by basically just changing the weatherability. And so this black line is the modern weatherability, and all the red is the sort of Monte Carlo simulations to get to this number. And here on the dashed line is what they figured out would have been 16 million years ago in the middle Miocene climatic optimum. And you can change your equilibrium PCO2 concentration by moving along this vector here. But this means that you're basically changing the weatherability. Something on the Earth's surface has changed to make it more weatherable, so you can have a higher weathering flux at a lower CO2 concentration. This was also sort of illustrated by Kump and Arthur in this chapter in this Ruddiman book in 1997. It's a great book. This is supposed to be bathtubs, and here's the tap coming in, and this is the drain. There's two drains. There's active origins and there's other regions, and you see here they've sort of illustrated this effect by if you change the amount of active origins, you can have a lower equilibrium CO2 at the same sort of outgassing. Another way to look at that, if you just want to have a picture in mind, is just the sort of soil type. And so this is a very extremely weathered soil here, bright red. There's very little left besides the refractory elements. And then you compare that to something like this. This is a grassland soil with a very thick molic layer here. Where there's a lot more capability to do weathering. So we'll come back to this idea. Like I said, volcanic rocks are also put forward, and this is a nice paper by Park where they've looked at the change in the Indonesian volcanic islands over time, over the last 15 million years. And as this has increased, the area has increased, they're saying this would actually be increasing global weatherability. These volcanic rocks of basalts are very easily weathered, and this could have reduced atmospheric CO2 for a similar weathering flux. But Claves-Rugenstein, they wrote a comment about this, basically pointing out that if this was the case, the seawater strontium isotopes would become more unradiogenic, which is not what they do. They become more radiogenic, which is much more of a continental signal, it seems. So the answer, we don't have the answer yet. People have been thinking about this for years, and there isn't really, we're getting closer, but we don't have the answer yet. There's a thought experiment I did, just thinking about how much silicate weathering could change with climate changes on glacial interglacial cycles, for example. And here I took the basalt silicate weathering law, which basically gives you CO2 consumption for a temperature and a runoff. And I took precipitation, modeled precipitation from Papua New Guinea. And this suggested that during the last interglacial, which was warmer than today and had higher runoff, that the silicate weathering CO2 consumption could be some 17% higher during the last interglacial. This is per kilometer squared, of course. So you have to try and scale this to an area. But regionally, this climate and a weathering signal should be recorded in the sedimentary record. Another way of looking at this, and so this is modeling results for the South Asian monsoon region itself. This is the models described in this paper, but the Wong Song, my colleague from GMR, he prepared this output for me. And what we can see here is the difference between the peak Eemian and sort of what would be almost now, and you compare that to 9,000 years ago and 0, so early Holocene. And so the increased insolation at these times is driving an increase in monsoon rainfall over the region, extremely strong increase in the case of the Eemian. And this is some 12 millimeters per day for the summer monsoon season. And this is, almost 1,500 millimeters per year. And, you think about that on this scale, and we could really be changing silicate weathering by a significant amount in this region if this was the case. The Himalayas, the orogeny itself, I wouldn't say we know, but I guess this idea is an old one, and then there's some more recent modeling results that sort of reinforce this idea here. And here they showed that the Himalayan orogeny and the South Asian monsoon domain rainfall, as you increase the orogeny over the last 30 million years, as you increase the height of the mountains, the monsoon rainfalls increased by some 400 millimeters per year in these models, which it's significant. And this, of course, you have to remember, is spread over the whole South Asian domain. And so in hotspots, like I showed you in the last figure, it could be even more. But did this orogeny increase silicate weathering? That's really the question. And Tara and Peter, they had this paper in GRL this year, which you should read if you've not read it, where they kind of re-explored this way of calculating the silicate weathering flux from the remaining cations in sediments. You need to know what the original parent material is, of course, which is a tricky question. But you can make first order estimates of how many cations have been lost to silicate weathering, and you can make then estimates of the consumption of CO2 if you know how the thickness of the sediments that have been weathered. And they have data for that for the Indus, Pearl, and Mekong, and they show here that basically there's some flat lines here across the last 20 million years. However, the Indus did display quite a bit of variability, and it was much higher. So there was higher silicate weathering CO2 consumption in the Indus catchment in the middle Miocene, and then that decreased towards the Pliocene. I mean, they say that this means that the uplift hypothesis, the Ruddiman hypothesis, isn't really supported, that the Himalayan orogeny did not increase silicate weathering, but I would argue that this timing here is perfect for the mid-Miocene cooling, which is actually the largest global cooling of the last 20 million years. Yeah, and you also have to factor in the organic carbon burial, like the Derry Francenor paper pointed out, is that when you have all these clays and you bury more clay material or even more secondary clay types, you can increase the burial of organic carbon, and this could easily also remove CO2 from the atmosphere, causing global cooling. So why IDPU 1443 here in the Bay of Bengal, in the southern Bay of Bengal on 90 East Ridge? Well, quite simply, this is the longest record in the region. It's the longest continuous record. We can go back to the Oligocene, and it'd be nice to have something closer to the source, but you're not going to get to this age with the cores we have. And this location here is maybe more sensitive to input from the eastern side, so Irrawaddy, Indo-Burma Ranges, Arakan Coast rivers. Then maybe if you had a core over here on the western part of the Bay of Bengal. Now, when we're talking about clays, this is the source to sink idea about, I took this cartoon from Romans, where you've got a forcing a signal, a climate signal maybe, and then a weathering signal. And then this is changed, this is altered a little bit in the transfer zone, which is the sort of the floodplains, before you can read it in the sedimentary record. Now, I've altered this a bit because we're talking about clays here, so it's not quite the same as erosion of sand material, say, and transport. We have to form the clays. A lot of these are secondary clays that are formed in the weathering environment, which is happening here in the soils and floodplains and not in the mountains. And then we have to deposit these clays somewhere. On the shelf, we can have reverse weathering, which is where we can make secondary clays as well. And then these particles are so fine that they can be transported a very long way in ocean currents. So basically, we need some mechanism to deposit these, and that will be as ballast in marine snow. So I'll show you that it is related to productivity probably. So the clays, I said they're formed on the floodplain and the shelf, and the evidence we have for this is from Lou Derry and Christian van der Noord in this Ruddyman book again. And here they've measured the hydrogen oxygen composition of the clays on the distal Bengal fan. And this is the meteoric water line, and then this represents the average smectite water fractionation. And here they've measured, these are the small clays here. Some of them, these are even smaller clays. They really did sort of fine separation. And then these are the micas, which are kind of showing a Himalayan signal. And what you see here is that some of these clays are really pointing to being formed on in the Gangetic plain. And there's nothing really plotting over here with a seawater kind of value. We looked at this well from the point of view of strontium isotopes, which I already said was much more strontium is much more mobile than these other isotope systems, and therefore it kind of reflects the composition of the weathering fluid that is forming these secondary clays. And here we've plotted the strontium isotope difference from the strontium isotope ratio of seawater at the time against the smectite composition content of the same clay sample. And we don't really see a relationship at all, which if a lot of this strontium was coming from seawater, we'd expect to see that. So it could be that there is secondary mineral formation on the shelf. There could be reverse weathering, it probably is. But the strontium that's being incorporated in the clays during this process is all terrigenous derived from the rivers. Okay, before we get into the data, another final sort of consideration is the paleogeography, of course. There's an active origin going on here right next to us. There's a lot of moving around. Since the from the Miocene, it hasn't really changed that much. But I do want to point out here, this pink and green is the Bengal Basin in the Burman Ranges, the Krishni Prism. And these are basically formed from eroded Himalayan sediments. So it shouldn't be a surprise. It's Himalayan material that was eroded in the Oligocene, perhaps, and deposited here, and then that's available for weathering. This is a bit of a finer scale version. This was from a paper looking at the Nicobar fan and how it started about 9 million years ago. But it really shows here how the Paleo-Brahmaputra was probably in a different place and not joined up to the Ganges, and the routing and the transport of sediment, and maybe where, especially the Shillong Plateau, there's a lot of rain there too, where a lot of the silicate weathering might be influenced by these changes, these tectonics, as the Indo-Burman ranges moved westward over time. Okay, I just said I talked about the sediment traps, so I just want to show this quickly. These are sediment traps in the Bay of Bengal, and we've got the lithogenic flux here in the middle, the wind speeds, just to show you the monsoon strength. And here's the carbonate flux. And what I really want to point out here is that during the summer monsoon, there's an increase in productivity, and then there's an increase, the lithogenic flux increases with that. Up here in the north, the lithogenic flux is kind of maybe driving itself, but it's also in sync with the productivity. Whereas here in the south, I think the productivity is packaging up these clays and depositing them on top of the 90 East Ridge. So with that in mind, let's talk about the records. So IODP site U1443 is a redrill of the ODP site 758. And what we did is we had three main cores and the fourth hole for the top. And when we piece these all together, this is the color scanning images here and the GRA data. When we piece these all together, we get this continuous splice on the top here. And then I was able to use that and go back to 758 and take the images and use this macros from Roy Wilkins and Igor software. And we're able to then line these up based on the color. And pretty much all the way here until the early Miocene, we can line this up very, very accurately, meter scale correlation. And this allows us to export the new age model, the continuous recovery to 758. So now we basically know how big these gaps are between the cores in 758A, which is great. You know, now we've got a continuous record, we can export this. And I wanted to make the point that if you're publishing IDP data, please give the core, the hole, the section, the interval, because without that information, it's impossible for someone to come and take your data and put it on a new age model easily. It's quite frustrating to not have that information sometimes. We have the age model based on the paleomag and the nanofossils like everyone else, but we also have, from the hard work of many colleagues here, high resolution benthic foraminifera stable isotope stratigraphy. So what I'm showing here is, this is the oldest part, so the early-ish middle Miocene, and we're comparing it here to a reference record from the Pacific, from the Equatorial Pacific, which has very nice sedimentation rates. It's a beautiful record. And you see here the red, the top red curve is the U1443. And you see here, despite these very low sedimentation rates, we have all the cycles, we have all the structures. So it's low continuous sedimentation. The same in the younger part here. This is from sort of 13.4 to sort of 8 million years ago. And here you see the correlation again. The carbon isotopes, you see that the oxygen isotopes are doing the same thing, but the carbon isotopes have a lot more structure in them at this time of the world. And this is a global signal that can be correlated. In this case, we're correlating to 1146, which is in the South China Sea, which was much more open back then. But again, this just shows how nice the record is, and that we can therefore come along and with this information say how quickly some changes are happening. This is the youngest part. This is the late Miocene. And for the full resolution data, more details, look at this paper from Clara Bolton in the Climate of the Past discussions at the moment. But what we have here in red is the site 1146 sort of reference record from the South China Sea. And then on top is our low resolution carbon isotope data and some tie points. And then I've got here the PMAG and the nanofossil datums from the shipboard. And these are all consistent with this age model of minimal tuning to this reference record 1146. So we're very confident of our ages. And, you know, when I say something changed within 100,000 years, we really know that. Okay, so provenance. Where do these clays come from? I'm only going to show this plot, which is neodymium lead, because the strontium, as I said, is more likely to be influenced by surface processes, weathering. It might be even the fluid composition, and therefore we'll focus on neodymium and lead isotopes, which are more particle reactive to really give us the provenance. The problem there is we don't have that much data for lead available. We were able to measure Irrawaddy clays from a delta core that Livio and Peter obtained. And this, you see, there's a bit of a spread here. but it's giving us a good number. And the other numbers that we have available are actually for the rivers themselves. So we're going to be plotting end members basically as the rivers in this case. And what we see is in the mid-Miocene intervals, and then also here in the late Miocene, we generally, everything's plotting in the same sort of area. It's a mixture of Irrawaddy-like, which could be not just the Irrawaddy, it could be the Indo-Burman ranges coming off the Arakan coast, or rivers even coming in through the Brahmaputra from this side. So I'm going to call that Irrawaddy-like in the rest of the talk. And there's a mixture. Of course, there is some Ganges in there, and one thing we thought about is this jump from the mid to the late Miocene is either including more Ganges, or it could be the Ganges end member itself has changed a bit, including a bit more lesser Himalayan material, but not very much. But overall, considering all the tectonic changes and everything, the mixture is remarkably consistent. And I would argue that this is because we're just weathering, the silicate weathering is happening where the rainfall's highest, and this is all old Himalayan material that was eroded and deposited in these basins and is uplifted to form the Indo-Burman ranges in this area. And this is where a lot of the silicate weathering is happening, forming these clays. There are subtle changes. So let's talk about the tectonics now, sorry. Tectonic events are long and slow. I took this summary here. So we're looking at these red bars down here from Allen and Armstrong summarized this. I'm sure there's lots of debate about exactly when these things happen, but the point I want to make is that these bars are very long and wide and cover millions of years. So first we had the high Himalayan uplift, the main central thrust. This is where a lot of erosion happened, probably filling in these basins. Then we have the onset of the normal fault here around the mid-Miocene. And the mid-Miocene, this sort of period between 14 and 10 is quite an active period. So we stop the uplift and it changes. There's a reorganization with the onset of the normal fault. We have surface uplift in East Tibet, and we have the initial thrusting on the main boundary thrust, all happening around this time. Of course, these are wide bars and it's hard to put strong ages on these. And then the end, this is also highly debated, but we have fast exhumation of the syntaxes starting up sometime in the last few million years. Now, ODP Site 758, you saw the change in color there, and this is reflected in an increase, exponential increase in the mineral flux to the site that happens here in the mid-Miocene. And you could say, okay, that's coincident with these changes in tectonics. There's also a change in the sedimentation rates on these two Bengal fan sites here. And we also found that there was a change in the amount of primary clay minerals delivered to the site, a quite drastic change in the case of illite. And you could argue this is maybe tectonic. But like I'll show you, this is also happening coincident with the global cooling step and changes in the global carbon cycle. So to try and unravel whether these changes could be tectonic related or whether it's climate related, we need higher resolution records, which is what we've done. But before I get onto that, I just wanted to point out or suggest maybe, put this idea out here that, if we've got a stable source of clays based on the neodymium isotopes and so, then this change in the clay mineralogy probably reflects a change in the weathering regime. And I looked around, and also in the South China Sea and Japan Sea, this is from Ali et al. If you need to find these references, sorry. They see a similar change in the reduction in the amount of secondary clays against primary clays. And, this is a different transport mechanism here, but it could be that this is a regional signal, and with Asia being so important for global sediment supply and silicate weathering, it could be that this signal is showing up in, say, seawater lithium isotopes here. This is a decrease in weathering intensity, and also the change in the strontium isotope. So this is the slope decreases here, which would be less continental input. So if you have a decrease in weathering intensity, you can have that. Though I do want to say that we still have more clays being delivered to ODP Site 758. Of course, it's one site, but we really need to have budgets across the whole bay and also on land to really say whether or not there's less intense but more silicate weathering happening in the region. So here's the high resolution data. These are our middle Miocene intervals. We have lead isotopes, neodymium isotopes, and strontium isotopes here. And what you can see is at the mid-Miocene cooling, we have a change in the variability. You see that here in the high resolution data. This in gray is the benthic delta 18O. This is this global cooling step here between 13.9 and 13.8. And the neodymium isotopes is much more variable and tends to have more negative, more Himalayan-like signatures before this event. And this change in variability, the reduction in variability, happens very quickly within 100,000 years. So, like I said, yeah, we have greater variability, more Himalayan-like, and then it becomes less variable and more Indo-Burman range-like. What could be driving this? Now, there is this tectonic reorganization at the time. This could have moved the orographic barrier further south, causing precipitation not to reach into these sedimentary series and the high Himalayan rocks so much, which could be restricting these sources. But ultimately, the timing, it's too quick. The time is too short for tectonics, and it's likely that this is also reflecting this global climate change of the global Miocene cooling. In the late Miocene, we also see, this is neodymium and lead, and this is now the carbon isotopes, the benthics, and this is a global signal in benthic carbon isotopes, which reflects some sort of reorganization of the global carbon cycle. And here we see a small, subtle shift, but measurable in the source of the sediments, also becoming more Indo-Burman ranges-like. And this is coincident with this delta 13C decline. And this also suggests there's a climate control. There's a shift of precipitation, or it could be that the precipitation elsewhere became weaker, and it was just making the silicate weathering still happening over here where the rainfall is most intense. Now, at the same time, the strontium isotopes don't change, and through here, the provenance isn't changing, but the strontium isotopes are. And so one way of thinking of this is it's not provenance change, this is some sort of weathering intensity change. And at the same time, in the region, maybe not so much in the east as in the west, but we have a change in the carbon isotopes and the carbonates, which is a shift from sort of tree dominated C3 environments to a C4 grassland environment. And this could cause stronger chemical weathering, we think, because grasslands have thicker soils. And just to sort of support that, there's this data from East Africa where they show the thickness of the soil horizon, and this increased over the Miocene. And here I have this picture of a moloch soil. So this is a grassland soil. And you can see here this thick layer where the influence of the grass roots is very strong, and there's a lot of organic material recycled. And this could cause an increase in weathering intensity, a small one. Now, another way of looking at weathering intensity, a new tool, and so this is all new stuff that's not published yet. And we're working on this with Jermaine Byron in Brest. Excuse me. Is coupled neodymium hafnium isotopes. And so these basically are a nice proxy of silicate weathering because the lutetium and hafnium have quite different partitioning in different minerals. Unlike neodymium and samarium, which are generally not fractionated in different minerals, lutetium and hafnium are strongly fractionated in different minerals, and the easily weathered minerals tend to be lutetium rich, and this means they're much more radiogenic. And so this radiogenic hafnium that's released during early weathering is incorporated in the secondary clay minerals. And this ends up giving us a clay array, which is more radiogenic in hafnium neodymium isotope space than the terrestrial rocks. And this is from Jermaine's work. He took world river clays from all around big rivers. Unfortunately, not the Ganges Brahmaputra or the Irrawaddy, but many other rivers around the world. And he found this relationship, which is always offset to more radiogenic hafnium isotopes because of this incongruent weathering effect. Another way of looking at it is here. And so, yeah, like I said, this is the terrestrial rocks all plot on this array. And then seawater is up here. And then this is the clay array, the global river clays. And Germain started plotting the delta epsilon hafnium clay. And so this is the difference between your sample that you measure and this global clay array. And when he plotted this delta epsilon hafnium clay against mean annual precipitation here for the different rivers and the chemical index of alteration of the sediments, he found there were quite good relationships, and that, you know, this is clearly a proxy of weathering intensity. You know, there are some things we still need to understand, but it looks like a very good proxy. And the main thing, which I want to point out, is that because we have neodymium isotopes involved in this, we are basically normalizing the source already. So any changes in source are being normalized out with this proxy. Okay, so this is our record through the Miocene. These are hafnium isotopes in blue. And then this is the delta epsilon hafnium of the clays here. And you see it's really quite high, +6, +8. It's variable there, it comes back down. And then here in the late Miocene, it starts to decrease, which would indicate a decrease in weathering intensity. And, you know, it also sort of mimics a little bit. I mean, we've already talked about taking out normalizing the source changes, but it looks a little bit like there's something going on here during the global cooling. Although it's very stable then afterwards, and it's really only decreasing here in the late Miocene. So I said these were quite extreme values, and that this is our data up here, our average. And here I've plotted two rivers from this paper from Fontenay, where they've looked at sediments from Madagascar, and you know, this is the tropical wet values here, sort of +3, and we're above that. So we're already beyond tropical and wet. And one idea is that here in Madagascar, the values changed from your sort of normal tropical wet values, although quite high, in the 1950s. Whereas after the 1950s, when there was significant deforestation, there was intense erosion, and the values in the delta epsilon hafnium clay have increased even more, and they're more like the values we find. So this could suggest that it's not just hot and wet and strongly weathered, but actually we also have intense erosion eroding the intensely weathered material and bringing it to our site. Further support of this idea comes from unpublished data from Germain from these two Congo River tributaries, where they have metamorphic rocks, multiple sedimentary cycles probably, and they have lixie soils. These are highly eroded soils, very old landscapes with tropical climate. And as these are eroded, we end up with these extreme delta epsilon hafnium clay values in the river sediments there. So this all basically suggests that we have a very wet climate, strong erosion, but yeah, strong weathering and strong erosion. Okay, and this is new. This is my last data slide, I say. And here's the hafnium record I showed you before from the Miocene. And then I've got one new data point here for 700,000 years ago, but this is important because it helps anchor it. And this is coming out sort of 3.6, which is exactly what you expect for a tropical wet climate with the modern river clays. And so it looks like we're ending up with something modern that makes sense. And therefore, what happened in the Miocene was either even more wet than today, with more intense weathering for sure, but also probably more intense erosion. And it could also be that we need to erode these intensely weathered terrains to get values like this. And so if we have more erosion and more fresh material, then we can't build up these extremely weathered terrains to get these values in the end. And then I've plotted this against the kaolinite percentage from Ali, from the Ali paper from beginning of this year, from 758. And you see it generally does track. The kaolinite is actually the mineral that's formed during the most tropical wet weathering, and therefore this would kind of support this. Although we need to think a little bit about the fact that maybe, you know, the Hathorne isotopes are sensitive to the kind of clays that we're measuring, and that's something we need to look at a little bit harder before we publish this. But yeah, I'd say this is a really nice way of supporting a change in the weathering intensity, a decrease in the weathering intensity over the Miocene to the recent. Okay, so my take-home messages are that there was a remarkably consistent source of clays produced by silicate weathering around the Bay of Bengal. This is most likely because there are these basins that are filled with Himalayan eroded material, and this is where the rainfall is most intense today, and it was likely that this was producing the silicate weathering since the mid-Miocene. There are subtle shifts in the provenance, which we can see, and these occurred very quickly around these Miocene global climate events, too quickly to be tectonic, and therefore we can see a link between silicate weathering and climate changes in the region. I would say that this decrease, the regional decrease in weathering intensity, we could probably say that maybe this is related to the initiation of the dry winter monsoon. It could be that this intense chemical weathering and erosion, the hot and wet Miocene, South Asian monsoon was more all year round, and then, you know, as we've come through the global cooling events, we start to have a stronger dry season, and this could also increase erosion and cause this change in the weathering regime we see. Okay, and with that, I'll thank you and take questions.
Great, thanks so much, Ed. That was a fabulous talk. I definitely have a lot of food for thought based on some of your results. And so I see that we've got a couple of questions already. I believe, Liviu, you mentioned that you had a question to me.
Hi, Ed. Hi, Tara. Hi, everybody. Very educational presentation. I hope there are students in the audience. It's like a class. Thank you very much, Ed.
Oh, you're welcome. Thank you, Liviu.
I have a question. I mean, I should know the answer, but maybe you'll give it to me faster.
Okay.
So the accretionary prism, that's the Indo-Burman range, should be Himalayan, but it's so different in signature, so it must have quite a lot of material from the arc.
Oh, it does. Sure. The arc material is in there. Yes.
So is it quantitatively big, or is just such a strong difference that even a small amount makes a difference?
Oh, I mean, that's hard to say. And of course, arc materials, arc rocks are more easily weathered and would be the first things to turn to clays and get transported. So it could just be that this is also this part of the sediments there is more represented in the clays that we're looking at. Yeah.
So why I ask this is that it really hard for me to imagine that you get such a lot of material from the Irrawaddy to that site. So I was wondering if there's not significant input signal-wise, not quantitatively in terms of amount of material, but from the Andaman region, from the Andaman Islands, archipelago.
I would say no, having been to the islands, and they are there's no big rivers there. It does rain, but they're covered in mangroves. I would say, and what we had to, mostly because of what the reviewer pointed out, is that all of this material here, the Shillong, the Suma Basin, in the Burman Ranges, all the way the Arakan rivers, we know from Christoph Collins' work and the stuff from Heather Stoll from the Pleistocene that the Arakan coastal rivers are draining the Indo-Burman Wedge, and they're putting a significant amount of material. There's a tongue of more radiogenic neodymium isotopes that sort of sticks out from the Arakan coast. And yeah, I mean, all this is kind of going to have signatures which look like the Indo-Burman ranges, and therefore the Irrawaddy. Yeah, so this is why I say Indo-Burman range-like, because it could be that it's also coming from the Paleo-Brahmaputra or from the Soma Basin and the Bengal Basin. And I think that is probably much more volumetrically important than anything from these little islands themselves.
Okay. That makes sense. Thanks.
I mean, the islands are themselves like the Indo-Burman ranges. They're uplifted accretionary prism. So yeah, you can't distinguish it.
I see. Okay, thank you.
I believe that I saw a question from Nagender. Would you like to ask your question?
Can you hear me?
Yes.
Ed, hello, how are you?
I'm good. How are you? Thanks. Nice to hear you.
Yeah, good talk. I'm a little question about the last slide you presented.
The last slide?
Paper. Yeah, the kyanite and the Hathorne isotopes.
Okay, this one, yeah.
Yeah. Is it not really puzzling that, it's completely, so continuously it's reducing the kyanite content as well as Hathorne isotopes values, which means the erosion has reduced, the weathering has reduced with time?
Yes, but the modern value at 700,000 years ago is plotting here. And these are the modern rivers, and so that's over here. So this is kind of the actual mean annual precipitation that we get in this region. So it makes sense from this point of view. So this, I would say that I guess you could have more rainfall than this, but it's already really an extremely wet tropical weathering environment that we have 700,000 years ago. And therefore, it could be that it was more extreme. It could be that it was for more of the year, or like I'm trying to explain is that if you have very, very strongly weathered material and you erode that and transport that, then you're going to get these extreme delta epsilon Hathorne clay values. So it could be that we just didn't have enough erosion back in the Miocene to bring fresh material. There wasn't such a supply of fresh material, should I say, and then we get more supply of fresh material, and then this is why we end up here with a modern, extremely wet tropical weathering environment sort of value.
Yeah, which means, but then the weathering should also be consistent with the rainfall, isn't it?
Yes, it is. It is. The modern, the 700,000 year value is consistent with a modern sort of mean annual precipitation over 3,000 millimeters per year.
Yeah, kyanite going down to less than 1% or something like that. It's a little surprising. Yeah.
No, it's 10%. It's 10%. It's 10%.
Yeah, the last one,
it's still
the youngest
still more than 10%. Yeah, it's still more than 10. I mean, this is the thing I also said, is that I would like to look into this more about how the composition of the clays could be affecting the Hathorne isotopes, and this could be important. Yeah, we need to understand that more before we start applying this proxy.
So how does it compare with the traditional geochemical traces of chemical index of alteration?
Hafnium epsilon clay, you see that here in this figure from the world river clays. I don't have that data yet for my samples. We
like potassium by aluminum ratios.
Yeah, well, we don't normally measure that. We just go straight for these isotope systems. But I do have some samples left over, and that's something that I think for this epsilon hafnium paper we wanted to try and look at, or at least a few of them, because there is this better relationship between the chemical index of alteration, which of course is itself susceptible to grain size effects and changes in the composition of the parent material. But yeah, if we normalize that out with the neodymium isotopes, this could be why there's a nice relationship here.
Can I ask one more question?
Sure. I don't mind. Are there any more?
Okay.
But yeah,
I just want to ask, how comparable is the 758 or the 90s Ridge site with the Andaman itself? You had NGHP 17, which you worked continuously for the last many years. For this time scales, how does the weathering records match or agree?
17, there isn't a lot of change. I know in the Lee paper they say there's a lot of change, but it's actually mostly in the smectite. The kaolinite doesn't change so much, and the kaolinite is the one that really forms during intense tropical weathering, and so the smectite changes could be subtle changes in the provenance there. But I have not measured hafnium isotopes in those samples. No, we haven't done that yet. We're thinking about trying to do some Pliocene work, but this is sort of at the proposal stage and nothing. But that's what we're thinking about trying to do next. So we might get more into the Andaman Sea sites and the sites further north too. Yes.
Yes. So that's the depot center for the Indo-Burman range of sediments, actually.
Yeah. Sure. I mean, there it really is the Irrawaddy. Although they do see some subtle changes in the provenance there. But I would argue that when they plot the clay mineralogy, it's dominated by the smectite change. And you always get this funny change where smectite and illite are always so closely correlated. Whereas I would say, look at the kaolinite, which is the one that is really reflecting strong tropical weathering in a wet environment. And that doesn't change that much, I don't think. I have to plot this all up together. Yeah.
Thank you, Ed. Good luck for your research.
Thank you. Nice to hear from you, Naganga.
Yes.
Okay, I believe there was one other person with their hand raised. If you have a quick question, I'm not sure. Okay, and then I believe Liviu, you also wrote that you had another question.
Hi, Ed. I'm going to put you a question that I put you many times.
Okay.
Maybe you reconsider now. We do not have good data from the peninsular rivers.
There is some data, yeah, but we don't have clays.
There is a huge Deccan province there.
Yes, but like you say, that there's also basaltic material. So I mean, there's a lot of smectite in these samples. There's a lot of smectite all over this part of the bay as well. And I guess there's more smectite here maybe than there is. You have to get very close to these rivers to get the smectite. Based on the isotopes of the Deccan, most of the Deccan, I mean, the Deccan has a very big spread in isotope values, but the volumetrically large parts of it are very radiogenic and neodymium isotopes, like they should be, like a volcanic rock. There's not a lot of crustal mixing in there. And this stuff would be, if you had a lot of it, if you had the sort of 50-60% of it making up the clays, that the smectite content suggests, then we would have much more radiogenic values. It's just not possible to do it from a mass balance point of view.
Okay.
This is why I think the smectite comes from somewhere else. Yeah, it isn't just straight from volcanic rocks.
Okay.
Okay, well, I believe that concludes this week for the Monsoon Seminar Series. So again, let's put our hands together for Ed Hathorne and your very, very interesting talk. I feel like I'll have to rewatch and definitely look up some of these new papers that you're citing and talk your ear off another time. So before all of you run away, please attend next week's seminar by Dr. Stephanie Tofeld for the Schedule A for next week, and that's October 13th. So again, if you want to receive Monsoon seminar emails, please just send me an email and I'll add you. And otherwise, I hope everyone has a nice morning, afternoon, and evening. And again, thank you very much, Ed.
Well, thank you all for listening, and yeah, bye.